Okay, today we are diving into the fundamentals of FPGA design and the VHDL hardware description language. If you come from a software or computer science background, your biggest hurdle won't be the syntax, it will be shifting your mindset. In software, we write instructions for a CPU to execute step by step. In hardware, there is no CPU. We are not writing code to be executed. We are using code to model actual physical structures, designing the copper pathways and logical gates ourselves. Everything in the hardware happens in parallel. Even when we write sequential logic, like state machines or clocked circuits, we are not telling a CPU to run lines of code in order. Instead, we are telling the hardware to synchronize multiple parallel actions to the tick of a clock. Our primary goal today isn't to master every detail of VHDL right away. Instead, we want to get our hands dirty with the toolchain. We are going to discuss the core fundamentals, jump straight into Altera Intel Quartus to create a project from scratch, write our first lines of VHDL, and run a complete simulation. By the end of this session, you will have a fully functioning development environment set up, giving you the foundation you need to explore the hardware design in future. Before we can synthesize logic, we need to talk about our tools. Altera, which is now owned by Intel, has a long history of devices and development boards, and because of this, the software environment can be highly version dependent. Let's break down exactly which version of Quartus you need for your specific hardware. We will also refer to the manufacturer as Altera Intel. If you are working with older educational hardware, like the original DE1 with a Cyclone 2 chip, you must install Quartus 2 version 13.0 Service Pack 1. It is the absolute last version that supports Cyclone 2. If you are using DE0 with a Cyclone 3 chip, then the version is 13.1. Obviously, if you want to use both Cyclone 2 and 3, then version 13.0 Service Pack 1 is the best option. If you try to use a newer Quartus version, you won't even find your chip in the device list. However, if you are using the DE0 Nano, which features a Cyclone 4, you can set up the modern Quartus Prime Lite version 25.1 or latest. Note that the modern versions offload simulation to external tools, while version 13.0 Service Pack 1 also includes a built-in simulator. Who is Terasic? Terasic is the official hardware partner for Altera Intel. A development board breaks out raw chip pins into usable switches, displays and ports for testing and prototyping. What does phased out mean? It is the commercial production of older boards like the DE0 to DE4 series, which has been discontinued because newer, more efficient chips took their place. These boards are incredibly rugged and active in thousands of labs worldwide. Because hardware description language, VHDL or Verilog, never changes, these penchant boards are still perfect for learning and prototyping. The software is still available. The free legacy version of Intel Quartus, like version 13.0 for older chips, are readily downloadable from Altera Intel and support these boards perfectly. This slide tracks an evolution from simple logic gate chips, for example Cyclone 2, to modern system-on-chip or SoC boards like the DE10 Nano that combines FPGA fabric with built-in ARM processors. When you download Quartus, the base installer does not include the actual silicon configurations. You must download the separate .qdz files for your target family, such as the Cyclone or Max2, and place them in the exact same directory as your main setup file before running the installer. If you skip this, Quartus will install, but when you go to create a project, your target chip list will be completely empty. To verify our designs, we need a simulator. If you are on Quartus 13.0, you will use ModelSim Altera Starter Edition. On modern Quartus versions, this has been replaced by Siemens Cuesta FPGA Edition. Both perform identical roles. They take our synthesized netlist, apply input waves, and let us watch the output waves. Make sure to download the starter or Lite edition so you don't run into enterprise licensing fees. Now that our environment is ready, let's step through the standard design flow. We will initiate a project, write our first lines of VHDL, and talk about mapping virtual signals to actual copper pins on our development board. And I am using the DE0 as an example. When you launch the new project wizard, pay attention to your folder paths. Quartus hates spaces or special characters in the folder names. Use underscores instead of spaces. Also, the name of your top-level VHDL entity must match your project name exactly. For the specific DE board you are using, select the correct part number FPGA. The example part numbers shown are for DE0, DE1, and DE0 nano boards. So just make sure you are using the right one for the specific board you are using. Selecting the wrong chip means your design will be compiled for the wrong physical package, and the pin assignments won't align. I've also included an example of the MAX2 devices, shown in brackets, as used on some of the popular low-cost development boards. Let's write our first lines of VHDL code. When we look at almost any VHDL file, it will always be broken down into these three essential parts. Number 1, the library at the top. Think of this as telling the compiler what vocabulary we are using. Here, we invoke the IEEE library and the standard logic 1164 package, so the system understands standard digital signals like zeros and ones. The second is the entity declaration, which defines the inputs and outputs. The entity defines the outside of our chip or device. It acts like a black box diagram, specifying the physical pins or ports. In this specific DE0 test example, we have one input button called key and one output called LED-G for green. The third part is the architecture, which is the insides. If the entity is the outside of the box, the architecture is what's happening inside the box. It describes the actual behavior or wiring. Here, it's incredibly simple. We are directly assigning the state of our button key 0 to our LED green 0. When you press the button, the light reacts. Now, let's look closely at the port definition at the top right. LED-G, out standard logic vector 0 down to 0. What does it mean in VHDL? This creates an array or a bus named LED-G with exactly one element in it, LED-G0. The Terasic convention. We named it LED-G because we are following Terasic's official naming convention for the DE0 board. If you look at the text file snippet in the center, this is a look inside the project's pin assignment file, the .qsf file in Quartus. Notice the highlighted line at the bottom, set underscore location underscore assignment pin J1 to LED-G0. This file acts as a translation layer. It tells the compiler whenever the user talks to LED-G0 in the VHDL code, route that signal to physical pin J1 on the FPGA chip. The hardware reality. If we look at the official schematic on the far right, we can see exactly where pin J1 goes. Physical pin J1 is hardwired through a resistor straight to the green LED labeled LED-G0. By matching Terasic's name style exactly, Quartus automatically handles the messy job of wiring our code to the actual physical chip pins. In VHDL, you can actually name this port absolutely anything you want. You could name it My Awesome Green Light. However, if you change the name, you then have to manually go into the Quartus pin planner and tell the software exactly which physical pin on the FPGA chip My Awesome Green Light connects to. So our key takeaway here is matching the vendor's naming conventions is a massive shortcut. It saves us from manually mapping pins every time we start a new project, letting our virtual wire seamlessly become a physical electrical pathway. For our simulation, we will not be assigning or importing any pin definitions. If we look at the statement LEDG0 followed by the less than and equal sign and then key 0. In software, this looks like a variable assignment, but in VHDL, that symbol is the signal assignment operator. Think of this less like a line of execution and more like soldering a physical wire between button 0 and LED 0. If you hold down button 0, the voltage state instantly propagates to LED 0. Note that on the DE0, as with many of the other boards, keys are active low, meaning pressing the button pulls the signal to ground or produces a logic 0. If you load this onto your board and the LED is brightly lit while you are not touching anything, don't panic, your code isn't broken, that's just active low hardware doing exactly what you told it to do. The correct way to describe this is LED 0 gets key 0. At the top of almost every VHDL file, you'll see library IEEE use IEEE standard logic 1164.org. Why do we need this? Standard VHDL only understands binary 0 and 1, but real silicon is more complex. What if a wire is physically disconnected? That's high impedance, represented by Z. What if two gates try to drive a wire to opposite states at the same time? That is an unknown conflict, represented by X. The IEEE library introduces the standard logic data type, which support these states, allowing us to accurately simulate real physical circuits. Compilation in Quartus is a multi-stage process. If you just want to check if your VHDL code has syntax errors or basic logical sanity, do not run a full compile. It takes too long. Instead, use analysis and synthesis. This does a quick parse and checks your syntax. Once that passes, running a full compilation will trigger the fitter, which physically places gates on the chip, and the assembler, which creates your final programming bitstream file. The two primary compiled output file formats are .sof, which is the SRAM object file, and that's for programming the SRAM, which is volatile, which is non-permanent, and the .pof, which is the programmer object file, and that's for programming the flash configuration device, which is permanent. Instead of programming the chip and checking it with an oscilloscope immediately, we use a vector waveform file, or VWF. First, we can create a new university program VWF. Next, use the Node Finder tool to automatically list and import your VHDL entities' inputs and outputs. Once they are imported, you can manually draw clock pulses or override signals with high or low values to simulate real-world conditions. Finally, we run a functional simulation to see how our output waveforms react. When the simulation completes, a viewer window pops up showing your input signals alongside the simulated output signals. Look closely at the timing diagram. If you toggled the input signal, did the LED output signal follow it exactly? In a functional simulation, there is no delay. The output changes at the exact same picosecond as the input. This is our safety net. If our logic is wrong here, it will definitely be wrong on the physical board. So we always iterate on the waveforms first. That brings us to the end of our foundational workflow discussion. We've officially gone from selecting our tools to creating a project, writing wire-level VHDL, and finally compiling and simulating our design. Now that you have the theory down, let's see all of this in practice using Quartus version 13 Service Pack 1. Okay, so if we've got Quartus 2 open, you can see I've got version 13.0. We need to start our project, and we use the project wizard to do that. So I go to the left, I go File, you'll see New Project Wizard, and it gives me the introduction. It shows me what it's going to assist me with. So it's going to help me with the project name, directory, the top level entity, the project files, the target device, and the EDA tool settings. EDA is electronic design automation. We'll talk about it when we get to that stage. So we go next. Important, we need to set the directory for the project. So click on the three dots, and I'm going to set it up in my documents. I'm going to right click, new, and I'm going to give it a folder name Altera, and I'm going to enter and select it. So now I can see that it is selected as the directory for the project. Next, very important, I'm going to set the name for the project. I'm going to keep it the same as the example, so DE0 _ test, and you can see it automatically updates the entity, the top level design. Okay, then we go next. Here we will add any files if we had any. We don't, so we can just go next. Here we decide which device we're going to use. Now in my case I'm using the DE0, so here you will select whatever you are using. If we go to the family, so there is the cyclones installed and there's the maxes. I know for my DE0 I'm using cyclone 3, and I'm going to use the filter to assist me now. I know that the package is a fine pitch ball grid array, so I've got FPGA. I know the pin count is 484, and I know the speed grade is 6. So that filters out my device. I can see there it is at the top, so I can select it and I can go next. Here the EDA tools are shown, so these are the external software tools we can use. In our case we're not going to use it, but if we had to set up the simulation we would do it over here. So we're going to keep it as is. We go next. Finally, it shows me the summary page. So it shows me the directory where I'm working. It shows me the project name, the top level entity. It shows me the family name, Cyclone 3, and it gives me the device part number. So it's 3C is Cyclone 3, 16 because it's close to 16,000 logic elements, just a bit lower than that, and it's 484 pins. The speed grade 6. So I'm finished, so I click finish. So now it created the project for me, and if I click on the DE0 test, I can see there's nothing linked. So I can say I need to add my VHDL file now. So that I do by going there and clicking on the left, new, and you can see VHDL file, and I say okay. You can see now the top level entity name is not the same as the file name. So when I say file, save as, Quartus picks that up and says I'm going to change the name to the top level entity, so that's great. So we keep that and save. Now I don't want you to sit and watch me type, so I've already done that. So I'm going to copy my VHDL and just paste it in here. Okay, so there's my library, there's my entity, and there's my architecture. All that's required now is to synthesize this. Now remember, we spoke about either we can start compilation or we can do analysis and synthesis, which would be faster. So when I click start analysis, it's going to say that the file has been modified. Do I want to save it? As soon as I say yes, it's going to start with the synthesis. Here on the left you'll see the progress, and it says successful. Okay, so that's great. Okay, I can see now from the compilation report that it shows me what it's done. It says it used no logic elements, which we do expect because there's no logic involved, and it's used 2 pins. The 2 pins we know is because we've got an input pin and an output pin, and that's it. So the compilation report will give us that summary. If you don't have it and you need to find it again, it's under processing, compilation report, there's the compilation. Okay, so if we now want to simulate this design, we need to add another file. So we go back, we say new, and here at the bottom we'll see university program VWF, and we say OK. So it opens up the waveform editor, which is empty. So we need to say edit, insert node or bus. It opens up the node finder, so I click find the nodes, list them for me. It'll give my ports that's in my design. I click on key and I hold in control and click on LED green and I add it. I go OK, OK, and it pulls it into the waveform editor. We can see now that for LED green, it doesn't know what the output is because it doesn't know what the input is. So yeah, I need to set the input. I have different options here at the top where I can set it as 0 or 1 or high or low, or I can use the count. So I'm going to click on count, and I'm going to stay with the defaults, count every 10 nanoseconds. We say OK. You can see there's my 10 nanosecond clocks. And before we simulate, I go simulation, options, and yeah, I set the Quartus 2 simulator. I say OK, and now it just gives me a warning. It says this is just for academic purposes, don't use it for timing. Fine, we say OK. Now we can go to the middle here. You can see run functional simulation. When I click that, it wants to save this waveform, and I say yes, and I keep the default, save, and then it opens the simulator and it gives me my output. Okay, so now we can see that the output is tracking the input exactly as we expect. If you want to zoom in, you hold in control and scroll the mouse, and you can see that the output is tracking the input. If, for instance, I wanted to change the input, I can go here and I can say, well, when the input is low, I'm expecting the output to be low, so I'm changing all of that. And I can go and say, run the simulator. The waveform changed. I say yes, save it. Runs the simulator again, and it gives me my output. Output is tracking the input. Okay, as expected. Okay, so let's just look at what the library function is with regards to the pins and the standard logic. So what we said is, because we have the IEEE standard logic 1164, we define a pin, an input and output pin, as standard logic, or in this case now standard logic vector. That means that technically we would be able to say to LED green 0 that it could get a high impedance. So that means I can comment out this line, and I'm saying I'm driving LED green 0 with high impedance. So if I do the analysis and synthesis, the file was modified, so I say yes, save it. It runs that, and it says it's successful. Okay, so you can see that definition definitely exists within this standard logic. If I, for instance, comment the library out and I do the analysis and synthesis again, you will see that it fails and it says not successful, and it complains about the object standard logic vector is used but not declared. So if I double click that, it'll take me to where the issue is, and that's at the very first part where it says key is in standard logic vector, but it does not recognize it because that definition is defined in the logic 1164 library. Okay, so what we can also do is we can define these as normal pins. If we had something like this and it's not a vector, then it's just standard logic. So I'm going to keep the library just to show that this still works. So I've got a standard logic pin key and a standard logic LED green. So it means that the 0 in front, which is the index, doesn't exist anymore, but LED green does. So this should still be fine. So if I go analysis and synthesis, it runs and it says it's fine, it's okay. Okay, so now it's not a vector anymore, it's just a single bit. Now it's still standard logic and I can still drive it with the Z. If I, for instance, don't have library, so I'm going to comment that out. So now it's going to complain about standard logic. So there we go. It says same object standard logic is used, but it's not declared. Okay, so the library gives us that definition. Something in VHDL that we can use is called bit. So we can change both of these just to say that they are bits. And that will still be fine, but the problem is that the impedance definition doesn't exist. It only exists in the library. So when we do the analysis and synthesis again, now it's going to complain. It's going to say character Z used but not declared because it doesn't know what this is. Okay, so that won't work. We can see still that this will be fine because we've got a bit as an input, a bit as an output, and we are saying LED green gets key, so this should still compile. So there we go. So it's still happy with this. Okay, so just a few combinations, permutations to show how the library ties in with the port pin definitions. Okay, I hope you find this helpful.